Good morning. Let's start today's lecture, and I'm going to tell about solutions of homogeneous linear systems. The first observation is that solutions of homogeneous linear system is a vector space. I recall what does mean vector space and vector subspace. At the end of the previous semester, we introduced the notion of vector space. This notion is natural generalization of the notions of the plane in the geometrical space which pass from origin of the some coordinate system. And in this way we introduced the set of n tuples of real numbers, and the set of n tuples of the real numbers is closed under the operation of addition and scalar multiplication. And this set was the first example of the vector space. And the notion of abstract vector space, I call definition of the abstract vector space. Let V be an empty set with two operations. First of them, vector addition. This sign. This assigns to any UV which belongs capital V sum O plus V. And second, scalar multiplication. Scalar multiplication. This assigns to any V from V and any real number K. K is a real number. The product and we have the following axioms for this operation. The following 8 axioms: commutativity, associativity. Existence of zero, of neutral element, which denotes by 0. For all V, W, for all V, W, U, for all V. For all V exist minus V such that V plus minus V is equal to 0. The addition axiom. Two axioms of scalar multiplication for all real number K, M and any vectors V, we have product scalar K and vector M times V is equal product of scalar which is equals product of K and V, K and M, and vector V. Here, the unit is a unit real number, and the last two axioms, the axioms of distributivity, which related these two operations, addition and scalar multiplication. The product of scalar K and sum of two vectors V and W is equal sum of scalar products K V and K W for any real number K and any vectors V and W. And last axiom, the product of the sum of real numbers K and M and vector V is equal sum of scalar product KV and MV for any KM real numbers and any vector V. Such definition was done in the previous semester, and we consider some typical examples of the vector space. And we have natural example of geometrical vectors in the space, and the vectors which parallel some distinguished plane in the space, and the vectors which parallel some straight line, and we have the examples of so-called three-dimensional, two-dimensional, and one-dimensional vector space. And the maybe main example of the vector space is the following example. The so-called RN, the so-called arithmetical vector space. The element of this set n tuples of real numbers, n tuples. And we can introduce the addition and scalar multiplication operations on this vector space by the following formulas. Vector addition. We have two n tuple A1, A2, AN, the first n tuple, and the second B1, B2, Bn. And by definition, the vector sum of this two n tuple is n tuple with element which is the sum of the corresponding element of this n tuples. First element of the sum is equal to the sum of the first element of adding n tuple A1 and B1. The second is the sum of second elements A2, B2, and so on. The last element is the sum of the corresponding element AN plus BA. And scalar multiplication is defined by the same way. The product of the number k and n tuple A1, A2, AN by definition is equal the following n tuple. The first element is the product k and first element of initial n tuple k times A1, the second element k times A2, and so on, k times AN. Easy to see that we have the example of the vector space. Easy to see that all axioms of the vector space are satisfied. Commutativity, easy to see if we change the order of the adding summands, we obtain the same result because the operation of addition of the real numbers is commutative, and A1 plus B1 is equal B1 plus A1, and so on. And we have the sum of the two n tuples A1, A2, AN, and B1, b2, bn is equal the sum in inverse order b1, b2, bn plus a1, a2, an. The same way we have the second axiom, axiom of associativity, so fulfilled because the addition of the real numbers is satisfied the corresponding axiom of associativity. The third axiom's existence of zero in the vector space can be, we also can to check and vector 0 in this vector space is an n-tuple which contains only 0. And easy to see that the sum of such vectors, the n-tuples which contains only 0, and any n-tuples is equal to this any n-tuples, and the third axiom is satisfied. The fourth axiom, for any element v1, vn, we can consider the n-tuple with opposite signs, minus v1, minus v2, minus vn, and the sum of initial n-tuple and the n-tuple with opposite signs is equal 0 n-tuples. The fifth axiom is also satisfied. Easy to see if we have two real numbers. First of them we multiply on the n-tuple, we obtain the following product, and let we have to k m and v1 vn n-tuple. By definition from other hand, we have and we check the fifth axiom, and sixth axiom is enough evident if multiply unit of the real numbers and some n-tuple, we obtain initial n-tuple. And easy to see that the two last axioms is also satisfied. And this main example of the vector space. And we have some derivative examples. We can consider some subspace of this vector space which the solution of some linear equation. The second example, example 2. let's consider the linear homogeneous equation. Easy to see that if we have two solutions of this equation, x 1 0 x 2 0 x n 0, and second solution y 0 y1 0 y2 0 yn 0. The sum of the solution x0 plus 1 0 x0 plus y0 by definition is equal the following n tuple. If we substitute the sum in the initial equation, we obtain that the sum of the first n summands is equal 0 because the x0 is solution of this equation, and the sum of the last n summands is also equal 0 because y0 because y0 is also solutions, and we have that the sum is also solution of our equation, and we obtain that on the sets of solutions of such linear equation, the addition operation is defined. The same way we can check that if we have a solution and any real number k, the product k and x0 is also a solution, because if you substitute this n tuple in the initial equation, we obtain the following. Because we obtain the following equality, and we obtain that the scalar multiplication is also defined on the solutions of initial equation. Let's denote this equation number one. Easy to see that the zero of the arithmetical vector space, the n tuple which contain only zeros, is also solution of such equation, and we obtain that 0, the set of solution of this equation, contains the 0 of the initial arithmetical vector space. And easy to see that the last axiom is also satisfied, because this axiom is satisfied for any element of arithmetical vector space. But the solution of our linear equation is also elements of arithmetical vector space, and because for these elements, these axioms is also satisfied. And we have the general proposition. The general proposition has some general definition. General definition. Vector subspace. Definition. I rewrite this axiom in this blackboard. Definition. Let V be a vector space and W be a subset of V. We will say that W be a subspace of V if W be a vector space with respect to the operation of vector addition and scalar multiplication. On V. And in our example 2, W is a set of the n tuples which satisfy the linear equation, homogeneous linear equation. And we checked that this set is a vector subspace of initial arithmetical vector space. And we have some general theorem about arbitrary vector subspace. Suppose W is a subset of a vector space V. Then W is a subspace of V if and only if the following conditions are held. A, condition A. For every UV which belongs W and any K and any real number K, we have sum U plus V belongs V, B, the product, the scalar product K, U belongs W, belongs W. This say that our subset is closed under operation of vector addition and closed under operation of scalar multiplication. And we can say that subset W is subset of the vector space V if and only if this subset is closed under the operation of vector addition and scalar multiplication. And let's prove this simple theorem. Easy to see that if our subset is closed under operation of vector space, easy to see if our subset W is vector subspace, the subspace of vector space V. The vector subspace, by definition, the vector subspace is vector space with respect to the operation of the initial vector space. If our subset is subspace, by definition of vector space, our subset is closed under the definition under the operation of vector addition and scalar multiplication, because by definition vector subspace, vector space is set with operation of vector addition and scalar multiplication, and by definition this operation define on this vector space, and it means that our subset is closed under this operation. And opposite assertion. Let our subset is closed under the operation of vector addition and scalar multiplication. It means that on our subset, these operations are defined. These operations are defined on our subset, and it means that these all axioms are satisfied, because these axioms are satisfied on the all vector space, but our set W is subset of vector space, and if the operation satisfies on the all set V, which also satisfied on the its subset W, and we obtain that in this case our subset is the vector space, and our theorem is proved. And in our example, we can check only two properties, namely that closeness of the set under the vector addition and scalar multiplication. Enough to check these two properties. And we obtain that the set of solution of one homogeneous equation is a vector subspace. And we have also some simple assertion, proposition. Maybe theorem 2. Theorem 2. Proposition 1. Let V be a vector space U W be vector subspaces. Then its intersection be a vector subspace. Proof. From theorem 1, it follows that sufficiently to check that the following two conditions, A and B, are fulfilled. We have two vectors, U and V, which belongs to the intersection of our subspace U and W. And let's prove that the sum of these vectors is also belongs to this intersection A. We have that U and W be a vector subspaces of our space, and V belongs U, and we have the sum also belongs U. U and V belongs W, and W is also subspace, and then U plus V belongs capital W. And from these two assertions, U plus V belongs capital V, U plus V belongs capital W, it follows that the sum belongs its intersection. The same way, let U belongs intersection K, B, and arbitrary real numbers. Let's prove that the product, scalar product K and U also belongs intersection U and W. The same way, U belongs W, K arbitrary real numbers, U is subspace, then the scalar product K and U belongs capital U. U belongs W, K arbitrary numbers, W is vector subspace, then K, U belongs W. And we obtain that KU belongs intersection U and W. And we obtain that intersection of them two vector subspaces is also vector subspaces. We can easily generalize this assertion and the same way to prove the following corollary. Let V be a vector space and U alpha be a vector subspace. Subspace for any alpha. We have some arbitrary family of the vector subspace. Then its intersection be a vector subspace. We can use, if set alpha is finite, we can use the finite or countable. We can use the reasoning on induction. In arbitrary case, we can use so-called transient induction. We can also repeat the reasoning which prove the proposition 1. Namely, if we have some two vectors which belongs the intersection of our subspace V alpha. From this fact, it follows that UV belongs to alpha for any alpha from A. And U alpha is a vector subspace. From this fact, easy to see that U plus V belongs to alpha from arbitrary alpha from A. And from this, it follows that U plus V belongs to the intersection U alpha. The same way, we can check that the item B is also fulfilled. Let U belongs intersection U alpha K be arbitrary real numbers from this fact Q times U belongs U alpha from any alpha, and from this we obtain that K U belongs intersection, and our corollary is proved. Let's return to solutions of homogeneous linear system, and from our corollary 1, it follows that the set of solutions of linear homogeneous system forms the linear subspace of arithmetical vector space. And let we have some homogeneous linear system linear system 2. And let's consider the set of solution of this linear system. let's consider the such n tuples x1, xn, such z every this n tuples is satisfy the every linear equation from our linear system. It means that this n tuple is solution of our linear system for E1, 2, and m. And easy to see if we consider capital Wi, the set of n tuples which satisfy the equation number I from our linear system. Easy to see that W is intersection of Wi. And we proved before that Wi is a vector subspace. Then W is also vector subspace. And this fact, it follows from corollary 1. And we obtain that set of solution of homogeneous linear system is a vector subspace of our vector space. And natural question, how to describe this subspace. We have some sorts of type description of the vector subspace. I call that notion of linear span of the sum vector. We can ask the following natural question. Let we have some arbitrary vector space where V be a vector space, and let capital V be a vector space and V be a some vector of the vector space. We can ask how to describe some minimal vector subspace which contains this vector V. Easy to see that if we consider only one vector, this vector is not vector subspace because if we multiply this vector on the arbitrary scalar, in general case, we obtain other vectors. Only if this vector V is equal to 0, only in this case we obtain that this vector is a vector space, because if we multiply this vector on the arbitrary real number, we obtain also 0 vector, and the sum 0 and 0 is equal to 0. Only in this case, one element subset is a vector space. In other case, we must only in arbitrary case we can consider this vector v also the arbitrary scalar product of this vector on the arbitrary scalar, and this product is also must belongs our vector space. And easy to see that the set of such scalar product is a vector subspace of our space V. And this set also denotes by LV, denotes or V, and is called linear span of the vector V. And linear span is a vector subspace. If we have some maybe finite set of the vectors v1, vn, we can also consider the set of the linear combination of all linear combination of these vectors, namely the sum of the scalar product of these vectors v1, vn onto some arbitrary real numbers lambda 1, lambda n. Easy to see that this set is a vector subspace. If we have some linear combination lambda 1 v1 lambda n vn and other linear combination mu1 v1 plus mu n vn, the sum of this linear combination is also linear combination, because we can, using the commutativity property of the vectors, we can group this element the following way: lambda 1 v1 plus mu1 v1 plus lambda n vn plus mu n vn, and using associativity and distributivity properties, we can rewrite in the following form. And we obtain that the sum is also linear combination of these two initial linear combinations. And from this fact, it follows that the sum of this linear combination also belong linear span of the vector v1, vn. The same way, if we can check property B, if k be an arbitrary real number and lambda 1 a1 lambda n an be some arbitrary linear combination of the vector v1 vn, the scalar product of the vector k and this linear combination is also linear combination. We used the axiom, we can use the axiom 5, and we can rewrite this sum in the following form. And we obtain that the product of the scalar product of the arbitrary real number and linear combination is also linear combination. And this linear combination belongs to linear span. And we obtain the linear span is also vector subspace. Easy to see if we have arbitrary subspace which contains vectors v1, vn. This vector subspace must contains also any linear combination of this vector, because arbitrary linear subspace is linear subspace closed under operation of vector addition and scalar multiplication. And from this fact, we obtain that linear span is contained in arbitrary vector space which contains the vector v1, vn. Proposition 2. Let W be a vector subspace of vector space V, and v1, vn also belongs W. Then linear span of this vector belongs W. Easy to see that if vector v1, vn belongs W, from this fact it follows that any linear combination of this vector is also belongs to W. From this it follows that linear span of these vectors belongs to W. So we obtain that linear span of the vectors v1, vn is a minimal subspace which contains these vectors v1, vn. And we will say that the vectors v1, vn generate the linear span, the subspace which contains this linear span of this vector, of these vectors. These vectors is these vectors form the generating system of subspace which contains this linear span of these vectors. I call the notion of the basis of linear independent system. What does it mean that these vectors generated the linear span? It means that any vectors of the vector space can be present as a linear combination of this vector, but not in unique way in general. I recall that we say that the system of vectors is linear independent if any vectors which can be present as a linear combination of this vector can be presented by unique way, and it means linear independence. But the condition that some vectors can be present as a linear combination is enough hard. But this property is equivalent to the property that if any vector can be presented as a linear combination of our vectors by unique way, this assertion is equivalent that the zero vector can be presented by unique way. And such way we obtain the notion of linear independence of the system of the vector. The system of the vector is called linear independent if the zero vector can be presented as a linear combination of this vector by unique way. It means the coefficient of linear combination which present zero vector contains only zero coefficients. And we obtain the definition of linear independent system of vector. Definition. Vectors v1, vn called linear independent and if from the fact that its linear combination equals zero, it follows that all coefficients of this linear combination are equal zero. It means that zero vector can be as a linear combination of this vector by unique way, only with zero coefficients. And if you have some linear independent generating system in the vector space, such linear independent generating system is called basis. In the vector space. basis. Linear independent generating system of vectors is called basis. A little later, we prove that if the vector space contains finite basis, then every basis of the vector space contains the same numbers of the vectors, the same number of the vectors. And the number of the vectors of the basis is called dimension of the vector space. Number of the vectors of the basis. The definition is correct because to any basis of the vector space contain the same numbers of the vectors, and this fact we will prove a little later. If we have some generating system, how to construct the basis in the vector space? We also consider this question, but also a little later. First of all, let's consider the question how to find the basis in the space of solutions of linear system. We have the following linear system and how to describe basis in the space of solutions homogeneous linear system. I recall the algorithm finding of solution, of general solution of the arbitrary linear system. First step of this algorithm to obtain the so-called reduced echelon form for this linear system. A11, A1n, A1, A2m be the matrix of our linear system. Using the elementary transformation, we reduce this matrix to the so-called reduced echelon form, namely to this form. After them, we use the Gaussian algorithm. We reduce this form to the following form: the columns which contains the so-called leading elements in this form, these elements which equal unit in the reduced echelon form. We reduced our matrix to the following form: the columns of our matrix forms the unit matrix. And we obtain this special form of the reduced echelon form. Such reduced echelon form in which the columns which contains leading elements form the unit matrix. And this form is equivalent to the general solution of our linear system. Using this form, we can write the general solution of this linear system. And this solution has the following form. Easy to see that x1 plus a1k plus 1 xk plus 1 plus and so on is equal 0, and we can transform the element of the equation which contains the variables xk1, xn in the right side of the equation, and rewrite the first equation in the following form: minus a1 k plus 1 x k plus 1 minus and so on minus a1n xn x2 is equal minus a2k plus 1 x k plus 1 minus and so on minus a21 x1 and so on. Xk is equal minus ak k plus 1 xk plus 1 minus akn xn. And we obtain the general solution of our linear system. And we can obtain the basis in the space of solution by the following way. Let x one the following solution. We obtain the following way. Let's put the variable x k plus 1 equal 0, and also elements we can calculate using this equation, namely let x1, x2, xk, the first variable will be so-called dependent variable, x k plus 1 xn be the independent variable. And let's put the value of the first independent variable equal unit, and also independent variables we put equal 0. And dependent variable, the values of dependent variables we can calculate, and in this equation we put the first independent variable equals unit, and other equal 0, and x1 is equal minus a1 k plus 1, x2 is equal minus a2 x plus 1, and so on. The last dependent variables is equal a k, or is equal a k plus 1. And we obtain the first solution. The second solution, we put the second dependent variable equal unit, other is equal 0, and dependent variables can be easily calculated, and its values is equal minus a1 k plus 2 minus a2 k plus 2, and so on, a k plus 2, and so on. And then last solution, x n minus k, can be calculated the same way. We put the value of the last variables equal 1, and other independent variables we put equal 0, and we obtain the values of independent variables is equal a1n minus a2n, and so on, minus a kn, akn. And we obtain the system or the solution of our linear system. I assert that the solution form the basis in the space of solution. Proposition, the last proposition in our lecture is the following. Proposition. The solutions x bar 1, x bar n minus k form the basis in the space of solution of linear system. Proof. We must to prove the linear independence of the solution and the fact that any solution of our linear system can be present as a linear combination of this solution. First, x1, xn be the solution of two. Let's prove that this solution can be present as a linear combination lambda 1 x1 lambda n minus k xn minus k. Easy to obtain such presentation. You can put lambda 1 is equal minus a minus x k plus 1 lambda n minus k is equal minus xn. Easy to see that if this solution I multiply, I'm sorry, without minus xk plus 1 xa, if I multiply this solution if I multiply the solutions on numbers x by k plus 1 x, k plus 2 x, n, xn. And to add these values, I obtain exactly the solution of the initial linear system. And the second fact that this system is linear independent. Oh, okay, I'm sorry, I haven't any time, and maybe the second fact is a easy task. You can let's prove that if such linear combination is equal 0, it means that all coefficients equal 0. Easy to see. I'm sorry. We have the following quality. Easy to see that if we consider k the component of our solution with the numbers of k2, this component is equal lambda 1 in the left hand, and in the right hand this component is equal 0. It means that lambda 1 is equal 0. The same way we can to prove that also component is also equal 0. And this reasoning is the ending, the proof of this assertion. And we proved that the solutions form the basis in the space of the solution of linear system. I have any time, maybe question. Any question? Excuse me, maybe quickly, most quickly, the ending of this reasoning. I hope that I repeat this explanation on the next lecture. Thank you for your attention.